So today's lecture is about recurrent nets and sequence generation. If these sound too strange to you, you're probably in the wrong class, so you may leave. Otherwise, I hope you enjoy my lecture. Also, make sure you ask questions throughout. There's probably quite a bit of material to cover, and obviously way more beyond what I'm just going to cover, which are the basics. But it's much better if we have questions along the way than to cover exactly in detail all the things I want to talk about today. And just a little bit of introduction. So I'm Oriol. I did my PhD back in 2009 in California, in Berkeley. And after that, I worked for 2 years in Google, but not in DeepMind. So I was in Google Brain, which is a group that works in the Mountain View office. So there I continued working on sequence modeling, which I started during my PhD. And then 2 years after that, I moved to London to DeepMind, where I have been working now for over 2 years. And indeed, sequences, recurrent networks have been like one passion of mine. So if something that I'm not talking about, you have some questions, we can talk about this during the break or later, and also you can email me. But in today's lecture, we're going to focus on both recurrent neural networks, which is a particular kind of architecture, and more generally, a bit of the overall big picture of how to deal with sequences in machine learning using more than other techniques, deep learning, as this is mostly a deep learning, reinforcement learning class. So let's begin by maybe giving you a bit of an overview of what we'll cover. I'm pretty sure you've seen these many times, and you might see this again in the future, but I want to give you a bit of my flavor and my sort of intuition and take on why deep learning is such an interesting topic. It's not one slide, but this will be quite brief. And then maybe why should you care about sequences? I think sequences are a very good data structure that generalizes many others. So it is important to understand how models like neural nets can input, output sequences and use sequences as an intermediate representation. And then we're going to go to a bit of the fundamentals. So we're going to start with the chain rule, which is more about the laws, the kind of things we optimize that regard sequences. Also, I'll talk to you about some of the issues of learning recurrent neural nets that make optimization slightly hard. So this is vanishing gradients. And then some architectures that are very much neural network architectures, much like values or other architectures you might have seen that are specific for sequences and specifically designed to avoid some of the drawbacks that I'll discuss. And then we're going to go to sort of a set of applications and very cool things that have happened very recently in research, things that have been deployed in production and so on at Google and elsewhere. And at the end, maybe we can discuss a bit of open problems and cool things, cool projects you can work on, or papers that are worth reading that are a bit more advanced, meaning more recent. So with that, I'm going to start basically with what is kind of obvious, which is deep learning is getting a lot of attraction. I actually last week was in Singapore and I talked to people there about this. They are very interested in artificial intelligence, machine learning, deep learning. And maybe the coolest plot here is this, which is the NIPS conference that happens every year. This is the registrations over time for the last few years. And there was some same growth happening for the last 5 years or so, as you can see here. So this is like 2 years ago, I guess 3 years ago, 2 years ago, and this was what happened last year, where even before the early registration deadline, which would be at 0, basically the conference sold out, right? So this is really showing that there's lots of interest. There's also a lot of noise, so you have to be cautious about what you read on the news. It makes me realize what I read about other fields, not mine, on the news that I probably shouldn't trust as much as I want to trust. But nonetheless, it's good to be aware that there is also noise, but also there's lots of things that have happened that were enabled mostly by the deep learning revolution, as some call it. So if we zoom out a bit on what deep learning, what are sort of very big pieces, So there's obviously platforms, or where do you run your models, right? So deep learning, as you probably know now, like it involves like training on some big data set and probably some amount of compute, parallel compute, GPUs, TPUs, and whatnot. So where do you run these models is something that strategically you have to decide, be it research or if you're a startup or a company and so on. So there are lots of platforms. There's also lots of frameworks that's very good for you guys, because there's lots of open sourcing happening in deep learning. So these are some of the most popular frameworks that allow you to try many models, also deploy them in production in your phone and whatnot. And lastly, there's also data sets, right? So, there's a lot of data available, and data is very important to drive these models. And, there's been more and more data sets open sourced that allow you to work on things like machine translation, which we will talk about a bit later. And if we zoom in a little bit, deep learning, you have to make a lot of decisions. You will see these more and more during the class and as you experience this during your research career. But there's even simpler things like nonlinearities, like ReLU sigmoids, GRUs and LSTMs we'll talk about today. The way you optimize these models, there's also a wide variety of choices to be had. Connectivity patterns, whether it be convolutional, which you've seen, fully connected, recursive, recurrent. The losses also play a big role. You might have heard about adversarial networks. There's also reinforcement learning, which is a different kind of loss. And obviously the elephant in the room, which are the hyperparameters, right? So if you train a model, you will be faced with many choices that there's almost like only good senses of what these hyperparameters should be, learning rate, all sorts of tricks, dropouts, gradient clipping, which is very important for recurrent nets and so on. So these are all choices that you will have to make as well as you start training these models. And these lists are non-exclusive, obviously. So this list goes, for hyperparameters, it actually goes off the slide purposely. So going back to the basics, deep learning has this very nice paradigm, which is we're not going to try to encode rules to do complicated things like detecting whether an image contains a cat or a dog. We're going to learn these from data. So we'll have a big data set, like an image and a label pair, and we're going to learn these functions via optimization of some parameters, and that's what Karen discussed a few weeks ago. And so if you have lots of data, you have these very big, powerful models like deep neural networks, convolutional neural networks, recurrent neural networks, and ideally lots of GPUs, then you definitely have lots to do, and there's been lots of profit made by many people. And one of these players have been Google, so this is a slide from Google Brain. Also, a quote by Jürgen, who told me that Google will soon be a big LSTM. So today you'll know exactly what he meant by that. Hogreiter and Schmidt-Huber invented the LSTM, which we'll cover today later. But indeed, at Google, many models that involve some sort of deep learning, convolutional networks, recurrent neural networks are being used. And this is a plot over time on the directories that contain some form of deep learning TensorFlow code in the internal Google repository. So there's certainly a lot of products that are using machine learning, deep learning in their core. So this seems to be okay. So then it's done, right? We know how to train models. We know convolutions are great for images. So are we done yet? And one of the things that especially 4 or 5 years ago was clear to us is that when the inputs and or the outputs that we try to train our data on was not of fixed dimensionality, right? So the images all had to be resized to the same resolution. The label space had to be the same. We had 1,000 labels for ImageNet, 10 labels for MNIST, and so on. So if that was the case, we knew pretty much how to do it. But the problem is when the inputs and the outputs are variable size, there start to be sequences. We start being annoyed, and there were some approaches that were not that clean. So I'm going to discuss what these were now, and then how we kind of almost unavoidably we went to recurrent neural nets, which is a pretty generic framework to deal with these sort of data sets and paradigms. So this slide shows why sequences, and I guess that my point is like everything is a sequence. So even this slide is a sequence because it contains words and a sentence. A sentence is a sequence of words. Then each word is a sequence of characters. If we zoom in, there's a bunch of pixels that describe each character. The pixels could be arranged in a sequence as well. And even this sequence of slides I showed also themselves are a sequence. So basically everything is a sequence in a way. It's a bit exaggerated, but if you know how to deal with sequences, you know how to deal with a bunch of modalities that are quite interesting. The obvious one is words and letters. So lots of sequence modeling has been done on language modeling, machine translation, and so on. But also speech recognition. Speech is obviously a very clear modality where you have a sequence of one-dimensional, like air pressure measurements that inform the sound. Images themselves, videos, touch, there's a lot of sequence-like data structures there. One of the cool maybe areas of research is programs, right? So some people attempted to compile programs or generate programs from some of these models, and programs are just sequences of essentially like instructions and constructs like control flow and so on. And also one of the maybe popular topics recently because of things like Go playing agents, reinforcement learning involves a sequence of decisions like how to drive a car or how to play Go or how to play a video game. And these sequence of decisions are related to each other so much that we need models that need to be able to integrate this information into a neural network or a model that remembers everything that happened in the past. So very, very briefly, these kind of models actually are running in production for example, for Google Translate, but also Facebook, I believe, and Baidu. These are neural networks that essentially translate, and I'll explain how this works later. You can do funky things like generating math or code. So this is Andrew Karpathy took a recurrent neural network and trained it on essentially math papers, and then could generate new math papers that look real, but obviously they're completely nonsensical. But you can read this sort of lemma and proof, and if you don't understand math, you might believe this is an actual paper, but these actually are not real samples from the real world. These are generated by one of these models that I'll describe. And also you can do other things like generating sequences from images that describe these images and whatnot. This is something that I worked also on back in 2015. And lastly, one of the cooler, maybe more extreme examples is that you know that convolutional networks are great for images, but actually you can also use recurrent neural networks, which sees an image as a sequence of pixels, like one at a time. So this would be like linearizing this image as x1, xn, and so on. And these models actually are also very powerful mechanisms to both input images and also generate images, as I'll describe later. And as I was saying, obviously DeepRL is another such example. So it is a bit of motivating. Why should you care about sequences? There's many more examples, and you should just go and Google it or Bing it or whatever. No biases. But as I was saying, sequences involve words, and words are by themselves also slightly annoying to think about in terms of using or inputting them to a neural network. So this is a bit of an aside of a very important conceptualization of how do we get a word into a neural network that essentially has these dense layers of features, right? Of 256-dimensional features that are compounded layer by layer. They are all like a vector of reals, basically. And a word is sort of something that's slightly annoying. That is, it's discrete, and it has it has a sequence of characters and so on. So one way to think about words, which is almost the obvious and the simplest way, is to think about a word as essentially a vector that is sparse, and you essentially have, let's say you have a vocabulary size of 10,000 words, unique words, and the rest you say, well, these words are rare, I'm going to say that they are unknown. So you essentially take a word and do the following. You say, well, I'm going to set a very long vector. This is longer than the usual vectors you have in convolutional neural networks. You might have 32 channels or 16 channels and so on. You take this maybe 10,000 dimensional vector and set a 1 at the position of the word identity that you arbitrarily set the word to, right? So if you have a large data set of text, you start by essentially processing it, building a dictionary or a vocabulary out of it. You take the 10,000 most common words in some order. It really doesn't matter the order. and then you assign each word is going to be a one-hot encoding of the position of, if like the word, let's say vocabulary is the word number 32, then it's going to be a 10,000 dimensional vector where the 32nd position is a 1, the rest are zeros. And then this is multiplied by a matrix that maps 10,000 to, let's say, 256 dimension or 128 dimension or some smaller number of a dense, which maps this vector that is very sparse representation onto a dense version of this, which is much less lower dimensional, right? So instead of 10,000, we go back to 100, which is in neural networks a reasonable size. And you have this very large matrix multiplication, which you obviously don't carry out because it's very sparse, right? So what you do to do this W times V, like V be the word one-hot encoding, this can be done very efficiently because it's just a lookup on which column of this matrix does the one correspond to, and that is what some people call word vectors, right? So this is a way to represent a word, which is this discrete structure, into a vector which is dense, like it's 100 numbers, let's say, and represents the word in some way, right? And in a very interesting way, if you do this, you now went from this discrete symbol that was a bit annoying to deal with to a 100-dimensional vector that we can now input into any neural network. And in fact, what we do with sequences is very similar to this intuition of mapping not a single word, but a sequence of words into a vector, as I'll describe later. But this matrix generally is obviously quite big because it has 100 dimensions times 10,000 or a million, right? Like there's actually a 10,000 vocabulary size would be far too small. In general, for things like Google Translate, for English, we use at least 1 million unique words because there's like all sorts of common names and so on. And more recently, people have dealt with characters as the unit, which then there's less of, right? We have maybe like few hundred characters if we consider many languages, and then we just encode these into the same way in a word embedding fashion. And the cool thing is, if you train certain model, which I'm not going to describe too much, you also can start doing vector arithmetic. So you map these words into this 100-dimensional vector, and then you start seeing these. This was a paper that was a skipgram done by Tomasz Mikolov et al. So if you vectorize the word queen and king, you can see, for instance, that if you subtract these two vectors that are 100D, these are similar to, for instance, if you subtract the word woman and man, and you can see then the neighbors of words are words that make sense and so on. So this is a very nice piece of work, and it really is the key because all the models that deal with sequences of language start with words, and the words have to be embedded into vectors somehow, and this is the way, and it's very simple, and you just basically think of a word as this one-hot encoding, and many libraries enable you to do these sparse multiplications to make this efficient and not super wasteful. So is this clear on how to deal with words or any sort of symbolic language that you might want to input to your neural network? Good. Okay, so remember this. This is important. But let's go back to the basics. So as I was saying, right, deep learning maybe annoyingly is so simple because it basically goes back to this, well, we can map X, an input, an image, or a sequence, hopefully very soon, to Y, which could be a decision from the image or from a sequence that is the translation of the input sequence and so on. And defining this mapping is sort of building a neural network architecture that can define these. And then we have also a loss. So we have a large data set of maybe paired examples, and then we define a loss, and we say, look, this function that maps X to Y needs to map X to Y from the training set as accurately as possible. And then we hope this would generalize. So for unseen images, we then hope it will classify cats and dogs correctly and so on. So in language, it's pretty much the same, right? We can think about, okay, like we have now our X is going to be a sequence of words, for instance, this. And then I can ask you, okay, who do you think wrote these? And you might know about literature and you might have opinions, but actually this was, again, written by a neural network. So these models start to be so powerful that they can understand how sequences of words are organized in a way that when you sample these models, they assign high energy to sequences that look almost like real data, right? And how do you do this? So the first approach to model sequences from a statistical standpoint would be to use what people call n-grams, okay? And n-grams are almost like intuitively obvious that would work to some extent, right? So imagine I'm going to ask you to model what's called language modeling. So your job is to decide which word comes after this sequence of words, right? So what to cook with broccoli and blank, right? And you might, if I ask you to write a word after this sentence that would make this a valid English sentence, you know, we can collect these papers, and then we have a sort of a small sample distribution from your belief on what should be the next word. We can also inversely look at how many times this sentence has been written in a very large corpus of text. So we can take, you know, all English books, all Google pages, indexed by Google, and so on, and also count of the times that I've seen this prefix, this sentence, what was the next word. And this is essentially what an n-gram model would do, where n would be here of size 6, right? So we have 6 words plus then a 7th word that we don't know. So we can literally look up for this prefix, look for the next word, and hope for the best, right? And this actually is not bad. As you use less words as context, obviously this works better and better because you find more matches in your large data set of language. But this obviously has problems. But this, nonetheless, this was a state of the art for language modeling for things like speech recognition and so on. And it's very simple and very intuitive. And in fact, back in the day, Shannon sort of did an experiment on how well can humans do these tasks, right? So if I ask you to give me the next character, well, that's what he did instead of the next word. So you know, imagine you do AN, and then I don't tell you that this is the next character. Most of you would say this is the next character, but maybe someone can imagine a different sentence. So it turns out that humans, if they try to decide on the next character, they do so with an error of 1 bit, right? So essentially, there's maybe, if you think about ASCII, there's 8 possible bits, 8 possible next characters, and humans are good, but not as good as, because they get it wrong sometimes. But obviously getting it wrong makes sense as well, right? Because you don't know what's next in any sentence, otherwise there's no point in communication, right? Communication, and that's what Shannon worked on, is transmitting information. So if you knew every single sentence you're going to read in your emails, I mean, you don't read your emails because you basically know what they would contain, right? So it makes sense that humans are not perfect at this task, but that's precisely how we measure how our models understand language, by measuring how many bits per character or bits per word we need to encode to compress sentences in a large corpus. So going back to the approach I was describing, we're going to take context like the cat sat on the, and then we're going to essentially count and do a probability distribution over what's the next word going to be like for this sentence. And math is very common. This is a very well-studied sentence that people use in these examples a lot. So math is actually 0.15% probability of happening, but obviously you can have rat, hack, dog, all sorts of words, and there's like words that probably you will never encounter, right? So the cat sat on the robot, maybe you don't see these in Shakespeare books, but this is a sentence that should have some probability, right? So we start to see a problem of this approach, which is there are valid sentences that I could creatively write, and most sentences I will actually never see exactly match in some very large corpus of text, right? So the problem of text, unlike images perhaps, is that there's a very long tail of sentences we will never encounter, and modeling them is very important, because when I write an email to someone, or when I want to translate an English sentence onto Spanish or French or whatnot, these sentences will not have been seen exactly in the training corpus. So we need to interpolate or smooth out these probabilities. And that's a lot of the work on n-grams was on how do you smooth out, how do you assign some leftover probability to sentences that have not been seen, yet I could imagine this sentence having high probability in a book about a cat and a robot that are friends and whatnot, right? So that's very important. But even if we say, okay, let's just do a very simple model. I take 2 grams, so I'm just going to take pairs of words, and I'm going to count their frequencies, okay? If you do that, well, you can just build a very big matrix, right, of counts, right? So what we would do is we have 10,000 words, so we have 10,000 by 10,000 matrix. Most of these counts are 0, right? So maybe we never encounter the word D followed by the word D, so that has a 0 count. Yes?
So I just asked on the previous slide,
yeah.
What's the difference between a 0 and a question mark?
So 0 is that basically if we have a corpus of text, maybe, I mean, okay, so this, we could presumably say this is not a correct sentence, like having D twice in a row. So we never encounter this in, let's say, correct English text. And the reason why we understand it is because this is an invalid sentence, right? This, you shouldn't write like that, or the cat sat on the sat, unless you somehow like sat is a name, like this is also incorrect, right? But there are also other words that we might not encounter in the text, but those would be first valid English sentences in a strict sense, and actually even probable sentence in some domains that maybe this data set of large corpus that we're doing this count study on wouldn't cover, right? So, you know, internet, I mean, there are all sorts of new words that every day appear, and if we now retrieve data from the 1900s, these words will have 0 probability, but we need to deal with the changes in language of the uses of words and so on. So there's sometimes the 0 makes sense to, okay, yeah, this is incorrect, so this has 0 probability. Sometimes 0 means, well, this is not common in this data set, but actually this should have been assigned some probability.
Okay, so this n-gram model also checks for grammar as well?
It doesn't check for anything. It's really, the model is the counts, right? So the fact that you don't encounter a sequence of words, a certain sequence of words might be because it's grammatically incorrect, but it also might be because these are rare words, and you will never encounter these many sentences. You actually will never encounter in any corpus, right? So it's the problem of a sparsity. And this in machine learning, and even if you have a very large data set, you always have this issue, right? I mean, if you, for instance, you've learned about images, so ImageNet has 1 million images. If I take an image of a dog, is that image exactly the same as anyone in the 1 million images of ImageNet? No, there's pixel by pixel, there's going to be differences. So that problem in images, which is a bit more, maybe you understand, oh yeah, of course, you're never going to take an image that looks exactly the same as another image. In text, this problem is a little bit harder because of the discrete nature of text, right? A slight change in intensity in some pixels, you might find, oh yeah, that's totally understandable. But here, telling you the cat sat on the robot, this is a sentence that has 0 probability in English. I mean, that's really like probably incorrect to say, right? It should have some probability. Yet I never encounter it in like maybe all the Google pages that I can index. But this is sort of the problem of data scarcity, which is prevalent in almost everything, images included. But in language, is definitely very important because language happens to be like very long tail, right? So many sentences will occur very, very few times. Okay. So as I was saying, like the approach of counting, which is sort of the thing you did before recurrent neural networks, in a 2 gram case, it's sort of works, right? So we have this 10,000 by 10,000 matrix. We count all the pairs of occurrences, which we can just do with some program, and then we have this very big matrix that is the probability of the word given some previous word, a single previous word. Now the problem is this doesn't scale very well. So if we have 10,000 words and we want to index not only the last word but the last n-1 words, we need an n cube of counts of these words, right? So these would be literally exponential in the number of words in the history that I want to keep, right? So if I want to say, oh, I believe language, which is obviously incorrect. I believe to predict the next word, I only need four words, right? With 4 words, I can tell you what the next word is going to be. That's incorrect, but even if you do that, now you have 10,000 to the 4 numbers or counts that you need to estimate. So there's a lot of data that you need to fill this matrix, and this matrix also becomes so large that you cannot fit it in any memory system and so on. So people Google actually released a data set of 5 grams, which was released some time ago, and it was 7 DVDs, okay? So this was, I mean, at the time it was a lot of data. So 7 DVDs where all it had was these 10K or a bit more to the 5 matrix of counts, many of which counts were pruned, right? So you don't actually write a 0. If there's no count, you assume that never occurs in your corpus. But that 5-gram model was actually a very good model because it was based on a lot of data, but it was also a lot of data, a lot of like information, very, very inefficient way to sort of compute these probabilities of words. And also very incorrect, right? So in this example, the cat sat on the mat. If I only allow you to see, for instance, 2 words in history, plus then predict what the third word is going to be, so this would be a 10,000 by 10,000 by 10,000 matrix. Well, you would have some model like probability of W4, the fourth word given the third and the second, then this probability and so on. So this we would look up in this matrix. But this model is super bad, right? For instance, if I give you the prefix on the, what's the next word going to be like? Well, this you would never say mat unless you knew that the actual sentence was the cat sat on the mat, right? So these independent assumptions are really bad in language and many other domains. Nonetheless, up to 5 words was what people used to do back in the early 2000s as a state-of-the-art language modeling. But this is completely bad because we make these independent assumptions saying, oh, you know, the word mad is dependent on the previous 2 words, but it's independent of the rest. I mean, if you read a book and I keep changing the name of the main character, you're going to probably be quite annoyed. And that assumes that there's an independence assumption of the previous like thousands and thousands of words because you know that the main character name was Albert, for instance, right? So these models really cannot do this, although this was what was done before. So what we really would like is for a model that didn't do or induce any independence assumptions. It's a model that, given all the previous context, all the sentences in the book that I've read until now, all the words that I read in the news article, those I want to consider to then predict what's the next word going to be like. And these independent assumptions kind of work because to a large extent the previous word and the 2 previous words are very important, but they're not sufficient to predict this very well. So what the chain rule allows us to do is to decompose this probability distribution over a sequence of words, which would require us to count this cube, right? That we need to basically have 10,000, 10,000, 10,000, and so on. Instead, there's this very nice rule, which is very similar to backpropagation, which you've learned in prior lectures. It allows us to decompose through Bayes' rule with the product of these conditional probabilities, okay? So the probability of the joint probability of all these words, let's say W1 to WT, is equal to probability of W1 times probability of W2 given W1 times probability of W3 given W2 and W1, and so on until WT, okay? And what does this allow us to do is to, if we can somehow compress this conditional probability, so the condition on W1, 2, and 3, we can somehow compress this, assume we can do that, then all I need to do is produce 10,000 probabilities for each of these products, right? So instead of having 10,000 by 10,000 by 10,000, I just need to do 10,000 at a time. So it becomes a sum instead of a product of things I have to model. And this actually is very easy to prove that this equality, and I leave the proof here, but it's really, really simple to prove this, that there exists a parameterization of this joint probability with these conditional probabilities. But the key insight is that now, if I have a model that allows me to do these conditional probabilities very efficiently, then I am in business. I don't need to drop words that are far in the past and so on and so forth. And the key insight here, which comes back from 2001, although these models were not very popular, was to vectorize context, right? So I want to have this probability distribution of WT given all the prior words, and instead of having this huge table, I'm going to have a function of these words. And that's basically what you do with neural networks, is instead of actually having the words be the unit of computation that you build the tables, you say, okay, I'm going to embed, the same way you can embed a single word in a vector, we're going to try to embed the sequence of words in a vector. And this vector, as long as it sort of is invertible in a way, can recover the original sequence. Now we can have a very powerful model that allows us to produce a probability distribution over the next word, given all the previous words, without making independence assumptions that are unrealistic. So the simple way that was proposed back in the day on how to do this was a bit naive, but that's kind of the premise to recurrent neural networks. And the way was, well, we know how to encode a word. This is just simply through word embeddings or this matrix multiplication that is very sparse. So in this sense, we can take the cat sat on the. This is a one-hot encoding of each of these words. So this is simple, like it's a 10,000 vector with only one in the right position. We're going to embed them into 100-dimensional vectors, each of these words. So now we have, in this case, 500-dimensional vectors. And we can simply, here I put something else, but we can maybe just sum these vectors, right? Summing is not great because any order will induce the same vector. But let's assume, for the sake of simplicity, that we embed each of the prior words and we sum them. This is a bag of words model, which is a very common model used in machine learning. Now, we just vectorize this variable sequence of words into a single vector. And now from this single vector, we can just simply, with a softmax, like we do in ImageNet, have this 100-dimensional vector that essentially compresses all the prior words and go back to 10,000-dimensional probability distribution that tells us what is the probability given this context of the next word. So the model would work as follows. You take the context, you convert it to a vector with maybe as simple as a sum, and then you have another matrix that maps from 100 dimension back to 10,000, and this 10,000 now defines a probability distribution over what is the probability of each of the next words. And because we have a large data set of these, we train this model by gradient descent, so we tune all the weights of this matrix here involved, so that the probability of the next word, which could be any of the 10,000 words, is maximized for math in this case, which is the observation, but maybe the cat sat on the floor would be also another sample we would get from this data set and so on. And we keep optimizing this, and now we have a very rudimentary neural language model that if we just take the sum is actually pretty bad because it again doesn't, if I permute two words in order, the model wouldn't know about that. But it now went from this 10,000 to the n massive tensor that we need to compute to just a few parameters of a neural network. So this is really the key insight of neural language models and the beginning of recurrent neural networks. Yes?
So this predates the Mikolov work effect.
Mm-hmm.
So are you creating those embeddings just through matrix factorization or something like that?
So these embeddings here for this model actually are trained so they predict the next word. So in Mikolov work, he did this kind of predicting neighboring words, right? But actually, in this prior work, they just trained these vectors for each word was initialized randomly, and then you just train these with stochastic gradient descent so that you predict the next word, which is very similar to skipgram, though skipgram predicts any word around you, and it has some contrastive laws and so on. Again, you don't need to pre-train these with matrix factorization. You train these end to end, as it is the case on almost all deep learning paradigms. So now from here to recurrent neural networks, it's basically a very simple change. So a recurrent neural network, so this, by the way, you don't take the sum. Actually, there was a matrix multiplying these 5 vectors. So this was assuming still that the context was of fixed size, which is pretty annoying. And if you take the sum, then it's not very elegant because the sum of 100 words of 5 words, the vector is going to be different with different dimensions and so on. So a recurrent neural network is a kind of architecture that essentially can read one word at a time into what people tend to call a memory. And from this memory, then all you do is predict what the next word is going to be like. So I'm gonna show it to you in this, and this is the simplest recurrent neural network that exists. So we have the word "the," that's the first word in a sentence, let's assume. We embed it with a vector. And then we have an initialized memory that could be empty. That's another vector. And then what we're going to do is we're going to take the memory and multiply it by a matrix W that is learned. So this is W times ZT minus 1 in, let's say, T is 0 here, so Z minus 1, maybe it's all zeros. And then U, which is this matrix that embeds the word into this 100-dimensional vector. So now these vectors, we sum them together. We do a tanh because we like nonlinearities in neural nets. And these we call ZT. This is the new state of the memory, right? So Z minus 1 was all zeros. Z0 is going to kind of incorporate the information from the first word, okay? And then from ZT, we're going to also train another matrix B, which maps from 100 to 10,000. That is going to try to produce a probability distribution that tries to match the data distribution. So in this case, the sentence is the cat sat on the mat. So these matrix B, the matrix U, and the matrix W are all learned. And in this case, for now, they're all trying to map from the word D to predict that the maximum or like the target probability should be assigning all the probability to the word cat. Obviously, there's many sentences that start with D. So eventually, you'll get a model that from D produces a probability distribution that follows essentially what typically follows D in the beginning of the sentence. Yeah.
Practice, is it common to have U and B be totally unrelated? In the sense, it seems counterintuitive in that
Yeah.
you're mapping from one hot vectors into this vector space,
Right.
and then you're going to map back out.
Right.
Shouldn't there be a connection between those?
Yeah, so some models, and in fact recently, maybe mostly because of regularization issues, but someone proposed U and B to be tied together. So U is mapping 10,000 to 100, B is doing the opposite, so you can have them to be the transpose of each other, or you can have them be close together and so on. So there are lots of people that try these things, and they generally help a little bit. And the most recent language model papers, especially if your data set is quite small, it helps a lot to have U and B be related. So that's a good question. So now we have this model that takes the first word and predicts the second word. That's kind of silly, but now, of course, because you have a recurrent neural net where you can take the second word, input it, and record it into the memory. So we have Z1 now, and from Z1 we try to predict the third word, and so on and so forth. So now we have a model that has all the nice properties we want. It can deal with any amount of words. This in particular will be a 6-word sentence, right? And also is order dependent, right? So the order in which we read the words will change the value of the word Z, of the vector Z. So because of the nonlinearity, you can verify that if I swap two words, I'm not going to get the same Z3, right? So this is simple to show. And again, it has this very nice property that instead of having this massive tensor that we need to have all the counts, it incorporates this by basically having neural nets and dense vectors represent any context, right? So this Z1, Z2, Z3 is the memory that so far has seen 1, 2, 3, 4 words, and it's trying to predict the T plus 1 word. And this is what a recurrent neural network language model is. And again, Mikolov actually showed for the first time in about 2012 or 13 in a paper sent to a speech conference actually, how these models outperformed by a large margin the models that were n-gram models, which essentially just counted from a big data set the occurrences of words given context. So that paper really convinced many people that these kind of models were very powerful. Unlike the previous model that maybe just sums the context, those models were cool, but they were actually not outperforming necessarily the n-gram models. But these models, after some training tricks and so on, started to really work well. So this is really the key insight. And then how do we optimize? This is just the same as you do in supervised learning. So we have a sequence of words. As I was always saying, oh, this comes from a data set. It's not only the cat sat on the mat. We have many such sentences, obviously, possible in English. So the way you optimize this is you have a big data set of, let's say, single sentences coming from news articles, for instance. And then for each sentence, for each sequence of words, we're going to have the model be happy or be highly, basically assign the maximum likelihood to the observed sequences of words, which is very much what you do in images, where you have an image and the label, and you want to maximize the log probability of that label given the image. So here it's the same. We want to maximize the log probability of sequences of words that we observe from some training set. And the way to optimize this there's several tricks, but essentially, once you lay out this recurrent neural network that reads into memory one word at a time and outputs the next word, much like so, this looks much like a neural network that we're used to, which has, maybe it's not a deep neural network per se, but maybe you can see it if you turn your head around, you can see, well, it's a deep neural network in this direction, which at every layer receives a new input, and every layer outputs one output, right? So a recurrent neural network is, in a way, now seen like this, a glorified deep neural network, except that the weights are shared, right? So the weights, the recurrent weights that are this W matrix, U matrix, and B matrices, they're all the same for each time step. So then if you have 5 or 6 or 7 word sentences, they all can be like processed by the same model. And then how you train it, you just do forward-backward algorithm, which is depicted, very fancily with these arrows. But essentially, you train these much like you train any model, with the caveat that there are some matrices that are shared, and the gradients are a bit trickier to compute. So is that clear? Like that once you lay out what's called the unrolled version of this neural network, it looks much like an image model, which receives inputs and produces output at each layer. Good. So I'm not going to go too slowly through this, but obviously it is important to at least once in your life derive some gradients. Back in the day, you had to do this every time you implemented the model. Now you have, whatever, PyTorch, TensorFlow, and people don't care about this anymore. And maybe we should stop caring about this. But let's for once think about what's actually going on when I write some program that produces this computation graph that is a recurrent neural network, but there are some gradients that need to be set to satisfy or maximize this log probability. So because of the chain rule, things are simple for the softmax layer, but a bit complicated for the other layers. So if we look at the chain rule, now not of probabilities, but the chain rule, which is backpropagation, we can say, okay, we have this probability of the word WT given all the prior words, and this is, the loss is just the sum over T of this, right? So here, basically, I'm going to rename this. This is for a single sentence, because the chain rule is the product of all these probabilities. In log space, it's going to be the sum. So that's fairly simple by putting the log into the product. And this, we need a gradient with respect to the 3 parameters, which are these 3 matrices, W, U, and B. So I'm going to just take for 1T this, right? So this is just taking one element of the sum out. And I'm just going to do like the chain rule of derivatives. So I'm going to say, okay, what's the derivative of this loss with respect to B, which is the B is the softmax matrix, right? So this is the 100 by 10,000 matrix. And this is just this derivative with LT with respect to P with respect to the logit, as we call them, and then this L with respect to B. And then you can see that this is very similar to, if you take the derivative of an ImageNet model at the topmost layer. So this is your model probability output minus the label. So if your probability distribution is the same as the label, you're correct. Then the derivative is 0. There's no need to update the matrix, times this CT transpose. And then for the whole loss, it's just summing these over T, right? So this is kind of almost batch, when you do batch computation, because these sums, the B's are sort of independent because they're at the top of these, right? So these B matrices are here. So this is kind of, you can almost see the softmax of each of the next word prediction. You can just batch these together, which is actually done in practice to speed up things. And a bit more complicated is the rule for W. So for interest of time, I mean, I'm not going to derive this, but you might be tempted to do the same as you did for softmax, which is, okay, so these I'm just going to derive it for ZT and so on. The problem is ZT, this derivative of ZT with respect to W, ZT is written here. So you say, oh, that's great. This ZT, the W appears here, so I'm just going to apply chain rule and that's it. The problem is ZT minus 1 also involves W, right? So you have to recurse this equation, and what you end up having is a sum inside, and it's very, very annoying to implement this. But as I said, this software does it for you. So, but you should derive it once and implement it in MATLAB or whatnot. So before we break for maybe 10 minutes, I'm just going to, since we're in the mode of derivatives, maybe it's not important how to derive it, but we'll see that these derivatives have some issues, right? So I'm going to talk about vanishing gradients, which regards, okay, we have this model, we have the loss, and we have a data set, and so what's the problem, right? We just optimize this model to assign high probability to the sentences, and success should be guaranteed. Well, the problem is there are what's called vanishing and exploding gradients, which were, again, studied in very old papers from Hogreiter, actually, before he invented LSTMs. Also, Yoshio has a paper on this. And maybe the way to see this, look, what does it mean to have vanishing gradients? I mean, n-gram models have very strong vanishing gradients. Why? Because if I look at only the previous word, then changing the words like prior to the previous word, I mean, it has no gradients because I assume they're independent, right? So in a way, you say, well, n-grams have very strong vanishing gradients, and it's probably okay for language to some extent, right? So in fact, for language modeling, as I was saying, Thomas Mikolov showed that vanilla recurrent neural nets without any trick were actually able to outperform n-grams already. But sometimes we need these RNNs to encode information and carry it over for many time steps, right? So we might, I might be doing something now, and maybe I'm like, I don't know, I'm very thirsty, but I'm not gonna drink water, but then tomorrow I'm gonna feel sick and I'm gonna feel, okay, I should have drank the water yesterday. So there's many time steps, but I can do sort of some learning saying, next time I have the water, I better drink it, right? And in language, that's perhaps not so important because words, previous words are very more important than so on, and than words more back in the past, but long term sometimes don't matter, and when it matters, then it's very important to understand this problem. So this problem, with removing all the nonlinearities and so on, it really resolves to like essentially basic linear algebra. So let's look at what a recurrent network, the hidden state, looks like, right? So we have this vector ht, which is going to be w times ht minus 1, right? So let's assume the network does not receive any new input, so this is just a network that has this hidden at the activation at each time step, and you just want to carry this vector forward. Now, if you resolve this recursion, you get that ht is going to be w exponent to the t, and this can be, let's assume it's a scalar, but obviously for matrices, this can be done as well, right? You have the matrix multiplied many times the first hidden state, h0, right? So what you can see here is that as a function of t, ht will explode, not even the gradients, right? The activation will not be stable if the w is large, right? You're multiplying a number by itself, and remember, this could be like 10,000 time steps we need to remember in the future, or way more, right? So that sort of is a bit annoying, right? So this is a very unstable sort of system, dynamical system, if the w is big, and if the w is slightly less than 1, then ht goes to 0. So you kind of forget very quickly as the value of w goes down. And remember, this w is not something we said. This w we learned, right? These are the parameters of the model. And in general, these would be matrices, so the same argument can be done with eigenvalues and so on, but even for the scalar case, you can see that there's a problem with these things, right? And so, but what we actually have is a tan h, which is not an arbitrary choice, actually. The tan h maps every number between -1 and 1, which means at least we're not in the case that these things can explode, right? But still, gradients can vanish, right? So we don't have explosions anymore, because if w times h is very large, we just say, well, it's +1, or if it's very small, it's -1. But then when we compute the derivative, right, so this is what the gradients, and if you do the chain rule, you get this 1 minus tan h square. So this is a number, again, between plus and -1. But then we get this times w here, right? So times w means, in theory, this could go to infinity, except that not really, because w is also in the tan h. So if you actually plot this function, you see that for the tan h activation in a recurrent neural network, you get essentially that the gradients are non-zero only in a very small fraction for the weights, right? So here is a small program, you can read this later, that I I derived like forward-backward algorithm for this very simple neural network that takes no inputs, and this is the value of activations as a function of the single scalar weight W that goes from -4 to 4. So it's obviously bounded between between 0 and 1 in this case, but the gradients are essentially 0, so there's no learning possible except for a very small fraction of the weights, which means really like, and what if you look at the research on recurrent neural networks back in 2012 and so on, you'll see that a lot of the problems were tackled with optimization, fancy optimizations techniques. So people were doing second order optimization and so on to try to deal with the problem that gradients were very sparse everywhere. And if you make the gradients not be so sparse, then you have these instability issues where gradients can explode, right? So this is really like a big deal, and that actually motivates not a solution that you can tackle through optimization, but a solution that you can tackle through changing the architecture. So instead of having this vanilla recurrent neural network with this tanh and so on, we will have a recurrent neural network that very elegantly will not have this vanishing gradients issue, thanks to essentially an architecture that was proposed a long time ago, but kind of forgotten through the 2000, which is called LSTMs. But before I describe LSTMs, let's take maybe a 5 to 10 minute break. And if you have questions, you can come here and ask as well. Yeah.
So, I always wondered how much you know whether people have tried just parameterizing the weight matrices to be orthogonal or close to orthogonal.
Yeah.
It seems like it would mitigate these issues.
Yeah, some people tried, in 2014 actually, there was a paper by Li Deng where they tried to make essentially the eigenvalues close to 1. The problem is it's hard to optimize this, right? So
you do manifold optimization because you know that those form a continuous manifold.
Yeah, so instead of that, they did just projected optimization, right? So they just optimize, they update W, and then they renormalize, right? But these methods somehow haven't really like been so successful.
Libraries for doing like manifold optimization.
Yeah.
Orthogonal matrices.
Yeah. So the simplest trick that I know works, or at least which was done by Thomas when he wasn't very happy about LSTMs because they're a bit complex. So he just took a recurrent neural net, and then half of the recurrent weight matrix, he set it to the identity, where instead of 1, he put like 0.95 or so, right? So those eigenvalues will be close to 1, and will retain memory for a while. And then the rest, the other block, like the lower right block, is going to be like any matrix. And he showed in some limited domain that this performs as well as LSTMs. But I don't know, people.
It's so much simpler.
Yeah, but no one is using this. So I don't know. Like I have tried a little bit to play with ideas like this, like playing with how do you initialize the recurrent matrix and so on. But honestly, like I just see the LSTM as sort of the value of recurrent neural nets. As in, like everywhere I try it, like it works right away. So I'm not, I tend to focus then on other problems, and I assume this is like as a given, right? So anytime I need a recurrent net, I just use an LSTM.
It's computationally cheaper as well.
Yeah. And GRUs are a bit cheaper than LSTMs and so on. But it's a good point. I mean, especially the paper from Mikolov that takes the weight matrix and sets a block to be diagonal. That's pretty clever. But even the results on that paper, they're competitive but not surpassing LSTM. So even that paper itself wouldn't empirically verify, right? Like he got like almost as good as an LSTM, which means no one will use it, right? Because everyone has these things in their libraries nowadays. But it's a good question, and it is one of the ways to solve this issue, right?
Because what I tried to do in a couple of different ways, I couldn't get it to work better either, and I just assumed it was my fault.
No. I mean, it might be your fault too, but it's not the. Yeah, there's other faults there as well. Yeah.
I was wondering, in your literally set ordering case.
Yeah.
You have the process cycle where you're sort of trying to remove the input order, right?
Yeah.
Why not just randomize a lot?
You can do that. Yeah. I mean, the problem, I think, if you do that, I mean, it's much nicer if the model has the right inductive bias to begin with, right? That's the motivation.
The idea being, you're not. It's part of the architecture that you are.
You don't need to learn that there is this such invariance. You might as well construct it in the model. And the amount it helped was not dramatic. So, but there are like follow-up works. I mean, there was even an IPS paper this year on sets and how to treat like a loss that is set aware, not like based on a sequence and so on. But I guess the short answer is, let's just have the inductive bias. If you actually don't have a sequence, you have a set, to have order invariance, right? Okay. But the fact that it works, it's because of what you said, probably. Like the fact that when you try to sort numbers, you don't need to permute each example via data augmentation. It will just happen naturally that the model should realize the order of the inputs don't matter. Like I like it a bit.
Because we had a class assignment where we that encouraged me to implement this.
I see.
It was sentence ordering, and you're ordering 5 sentences in a story.
Okay.
And you kind of build an LS and I mean a sentence embedding out of each of those.
Yep.
Then combine them using. But yeah, it didn't work.
Using a variety of techniques. We tried using sequence to sequence all the time.
I see.
Very well.
Okay.
But tends to have a big problem with projecting models.
Yeah. Although someone seemed to get it.
Okay.
I couldn't, with the longer non-class, someone could just re-implement it with paper.
Okay.
I don't know. Do you have thoughts on what?
So but this was like given 5 sentences, you just essentially point to the order, like you just say 3, 2, 5, 1. Or like, okay, I see. Yeah, I don't know. It's a cool problem. I mean, these things. There could be so many things wrong with the model, right? So, but yeah, I think the model. So you had the softmax over 5 digits, or you had the pointer network?
I had a pointer.
Okay.
Yeah.
So you have a dot product between the 5 sentences and then
a learned infection.
Okay, and then you just have some initial vector that points to. Okay.
Exactly.
I mean, that should have worked. I don't know.
It could be that I got it.
Okay.
Tried softmax.
Okay. Yeah. So I mean, if it's always 5, softmax might work. Even might be very almost the same as the pointer mechanism. But yeah, it sounds like it's a cool data set and a cool way to learn embeddings of sentences actually, right? Because I mean the task itself it's kind of skip grams. I mean the task is silly, but like what you get out of it might be quite nice, right? So
I mean, I guess in terms of applications, you have coherence modeling as a potential application. The correct order should be the most coherent.
Yeah. So it didn't learn at all. It didn't know you couldn't overfit a small data set. And okay. I see. Okay. Yeah.
One thing I tried in order to enforce uniqueness, because there was a regular problem with predicting 2.
Oh, I see.
Was if it predicted a duplicate value, shuffle the inputs and make it try again.
Okay.
Because obviously it's ordered standards, but if you give it a different ordering, it shouldn't predict something that's wildly far away from it.
Right. But in the decoder, was it autoregressive? Because you should learn very quickly that you never repeat a digit, right? So I guess you have a pointer, but I see.
Well, your standard decoder is autoregressive.
Right. But if you have a pointer, like you point to like let's say sentence number 2, and now you have to output one of the sentences that's not 2. So at training time, how did you let the model know that 2 was already output? Did you input a 2 or?
Yeah, so I think this was my mistake. I input the correct sentence embedding.
Okay, that's fine. No, that's fine. Well, that's okay. That seems fine. Yeah, that seems better than actually the number. So you do really like pointer nets where you input like the embedding that you just pointed to basically. Okay.
An evaluation, what do you do?
An evaluation, you just take the initial the end result of your process step to initialize the decoder, and then you feed in turn what was predicted into.
But do you enforce like that it has to basically be a permutation or not?
No, I didn't. Well, I did through a not totally non-differentiable graph. Like,
Okay.
Belief propagation, loopy belief propagation.
Okay, but you get, but I see at inference, like the simplest thing is to just prune away, like from the beam search, like the things that are not valid, right? So,
maybe that was,
yeah,
maybe
that's what you can do for advanced models, like for the parsing model, especially that it had to output a tree. If the output was not a tree, you just basically prune out the softmax. Right? So if you know, like for instance, I mean, if you output a 1, or like imagine like the output order is 1, 2, 3, 4, 5, you output a 1, then the next softmax at test time you just mask out the 1, so you sample from the other, or take the argmax, not considering 1, so you are guaranteed to always output a permutation. But that should have been learned, right? I mean, that's
it should,
yeah. So
data, although it wasn't that bad.
okay.
Thanks a lot.
Yeah, it's a cool application. It's too bad it didn't work. Yeah. Oh, okay. Hey. Oh, hola, ¿qué tal? Sí. Molt bé. Fas tot a punt de deep learning? Sí. Sí? Bueno, està bé. Home, és bo tenir cursos d'aquests. A l'OPC estan fent ara també. Sí. Però em sembla que és de màster també. Però bueno, fins i tot allà ens modernitzem, que està bé, perquè a vegades els programes aquests d'undergrad són molt antiquats. No sé, jo vaig fer telecos i vaig aprendre moltes coses que no eren molt útils. Sí? No? Igual millor que telecos, que vaig aprendre moltes coses. Bueno, convolucions almenys. Tinc un grup d'investigadors del DeepMind que fan diverses coses, però estic ficat bastant amb el tema de StarCraft. Estic liderant aquest projecte, tinc una transparència al final. Però sí, tenim, no sé, una mica, ja et dic, per exemple, l'Aaron treballa amb mi, llavors ell ha fet coses com WaveNet i coses així, que ara també faré una mica d'això, però sí, faig moltes més coses que feia quan vaig començar a Google, que era més sequence to sequence i tal, però és divertit. No sé si comencem ja. Sí. Okay. Let's start, guys. All right. Please take a seat. All right. So to recap, we learned how a recurrent neural net has this vector that it keeps updating with new inputs, and how this vector is also used to predict what's coming next for language modeling, for instance. But also the chain rule, the backpropagation chain rule, induces these kind of unstable learning paradigms where gradients go to 0 or explode if we're not very careful. So despite many efforts in optimization to deal with this, which many of us worked on back in 2012, and perhaps fueled by these new frameworks which allowed us to not care too much about computing the gradients and so on. These models, deriving the gradients is quite complicated. Actually, I remember when my first recurrent network that I had to actually implement the gradients myself in 2011 was quite a complicated one. And I talked with my friend Ilya, who also did a similar derivation. And then we all said, oh, there's these new models, or like actually old models, but no one uses except for Alex Graves, who will give a lecture later here, which are called LSTMs. But implementing the gradients is such a pain that we're just not going to use it. Instead, we're going to implement second-order derivatives. So not only we had to take the derivatives or compute the derivatives of with respect to all the matrices, we had to compute the Hessian, which was not simple, but it was simpler to implement this. But what is the intuition behind this model that is called LSTM, which stands for long short-term memory? This paper was from Hochreiter and Schmidt-Huber. And again, these models were only used and repopularized actually by mostly a paper that we wrote in 2013, which I'll explain later, with actually Ilya and Kwok and myself, so which called sequence to sequence. So the main idea of this model is that, and I'll skip to that, is that, well, okay, like we have this memory, and instead of being a vector, which is the tanh of the sum of the input times some matrix times the prior state times some other matrix, it's going to be a much more complicated sort of formulation of integrating information from the past and from the current inputs. But the main thing that makes learning long-term dependencies much easier is what's called the forget gate, which works as follows, right? So now we are zooming in into one of these boxes where it takes one input and it produces one output. And this box, instead of having a single vector going in and out of a state, it has two vectors, which are referred to as a state, which is maybe similar to the previous state, and a cell. The cell is just it's some other name to another vector. These two vectors generally have the same size, 100 to 200 dimensional and so on. And there is an input that it enters this block. So that's again zooming in, right? So the main insight here is that we are gonna take the prior state or the prior cell CT minus 1, okay, and we're gonna simply sum these to produce the next CT. We're gonna take the sum of the prior CT minus 1 plus some input that comes from the input XT and HT minus 1. So this would be without the forget gate. So forget about the forget gate for a second. So there's no forget gate. So we simply say to the recurrent state, we're just going to add something new every time, right? And that actually is quite powerful, because if we always keep adding to this recurrent state, then to think about, imagine I add the glass experience, right? I add it, and then I keep adding things, right? If I have to connect something that happens tomorrow to what I'm doing now with this glass, there's basically 10,000 vectors that I've added one after the other. So this space is pretty busy in terms of there's many vectors that I've added, but the vector that is relevant is there. It's just there as a sum, right? So if you think about how the gradient or the information flows, there's one out of these sum elements of a sum that I can just backpropagate and learn from, right? And this is the sort of the key insight about always adding to the hidden state instead of multiplying it by a matrix. As soon as I multiply it by a matrix, I basically get into this eigenvalue issue where if multiplying a matrix many times by itself sort of has this issue of a decaying effect or exploding effect, which is worse. So an LSTM, instead of adding always, it has a gating mechanism, which actually in equation might be a bit simpler to describe, and I have that later, which says I'm going to add to the state, I'm just going to add the prior state plus something new, but how much I add or I keep the previous state is gated with a number from 0 to 1, right? So I'm not going to just have CT be equal to CT minus 1 plus some other thing. I'm going to have CT be equal to CT plus minus 1 times a function that is between 0 and 1. And that's sort of one of the key ingredients of this new recurrent cell that is able to now remember for much longer. Another thing that people found unnecessary but was in the original paper is also how much do I want to pay attention to the new input. It might be that I receive a new input that I don't want to actually get into my state. So there is a way to gate that out, to say I don't want to read this input, but that turned out to be not that necessary. And then there's another gate that controls how much do you output from the state out. And again, this is not that important, but in the 1997 paper, these were all like elements, and this model is like quite complicated, right? So each of these each of these things like has a matrix. So now if you have to think of backpropagation here, it's quite a complex thing. But TensorFlow or any other framework to the rescue, implementing these nowadays takes essentially these few lines of code, and this gets all the gradients and so on right. Yes?
Well, I have a question about like when we
Mm-hmm.
Why are we using the H1 rather than the C1?
That's pretty arbitrary. So I wrote the equations of what I just described, but using H versus C is a fairly arbitrary choice.
The C is the latent variables.
No, both H and C are hidden, like are the memories. So the memory of this system. So let's maybe describe it in equations, right? And then we'll go back to your question. So there are 3 gates that we need to compute, and the gates are going to be essentially so each W here is a parameter. So there's many new matrices that appear, but the input gate is this. It's basically some matrix times the input plus another matrix times the previous time step t minus 1 plus a bias, right? So this is similar to to a recurrent neural net that we just described. And then I'm going to have 2 more of these with different matrices, right? So these matrices, these and these matrices are all different. And they all control the flow of information in this LSTM. One is how much do I keep my prior state into the next state. The other one is how much do I care about the input. And the other one is how much do I output from the current hidden cell. So these 3 things plus then the output, this is actually the output gate, have this, you then update this CT and HT, right? So this is all like HT minus 1, and there's a version that also has CT minus 1, which many people drop, and we did also in our sequence paper. So this would be like sigmoid, which is a function that maps the forget gate between 0 and 1, dot product, element-wise product with CT minus 1. So here, if the forget gate is always on, then CT is always CT minus 1 plus something, right? So that's the part that crucially allows you to integrate out information from many time steps ago. Then this is the gate that controls the input, so that's why it's I. So this other gate says, oh, there's this new input information J, but I might take something into account or not. This is not so important. And then HT, which is how do we update the state, is just simply like, this is the what would be the output, HT. Then you do a softmax on top. So this, you just get the output gate times tan H of CT. So this is a bit arbitrary, some of these choices, but that's what the LSTM is. And then in code, because we don't need to compute gradients anymore, this if you zoom in when you see the slides, it's essentially these equations written in TensorFlow, which is very, very simple. So in 2014, maybe perhaps in a very kind of clever way, Cho and people from Montreal proposed a new kind of cell, which was more simplifying some of the elements of the LSTM, which essentially, and the main element here is that I need to very easily be able to retain whatever is in the memory, right? So this forget gate is super crucial. And what they did is there's less equations and there's a bit of less parameters and it's a bit less computationally expensive. But what this is about is basically X is the new input, and then there is essentially a choice between maintaining the previous input here and ignoring the new input, or ignoring what was in the hidden state and just switching to only receiving the new input X. And in equations, this looks like this, right? So this thing is the key element, which is the next hidden state HT is going to be 1 minus Z times the previous state H. Their notation here is slightly different. Plus Z, right? So there's not 2 gates here. The one gate is 1 minus the other, but this is also between 0 and 1. It's a bit of a simplification. Times HT minus 1, right? So HT, this is the one that enables the long-term dependencies to flow, and then this H hat is the one that sort of gets the new input and produces a hidden state that depends more heavily on the new input. But essentially, this GRU is another kind of LSTM, and people use both, and there's lots of papers studying which one is better. The truth is, LSTMs and or GRUs are way better than the first version of the model, which simply had the tan H and the sum of the 2 matrices times the vectors, one from the input, one from the previous hidden state. That RNN really doesn't work. We tried that for translation and so on, and because there you have to maintain things in memory for a very long time. it really failed, and the key insight to make many of the models I'm going to present next is to use these. And as I was saying in the break, you can think of GRUs or LSTMs as sort of the building block of recurrent neural networks, much like you can think of ReLUs as the building block of more model or residual connections, even as modern convolutional neural networks or deep neural networks. And in fact, if you think about residual connections in a convolutional neural network, these are shortcuts between the input and the output, much like you can shortcut times, like many time steps ago through this mechanism, because if you always have the forget gate on, meaning you don't forget, I guess, then you always map, so from H, let's say, time step 100, you have all the previous time steps summed, which is very, very similar to having residual connections to every time step in the past. So this is really like the key insight, and what deals with long-term dependencies and deals with like sort of optimization issues, which maybe wrongly so the research community focused on solving with optimization, and it turned out the solution was change the model, not the optimizer. And changing the model turns out to be very powerful, and many new modifications to recurrent neural networks are based on modeling improvements, such like attention models, which you will know about or learn about a bit later. But I'll touch upon a bit superficially later on. So this solves the issue of vanishing gradients, but actually if you train these models, you still get sometimes like not a number gradients. And then the simplest thing to do, which is kind of annoying, but it's a super simple trick, is if the norm of the gradient is too large, you just clip it. So that code, and you always clip it to 5, by the way. That's my secret. So I'm not kidding. I tried this for like so many tasks, it always works. 5 if you divide by batch size, okay? Otherwise it's different. So for an LSTM, 5 works very well. But I'm not kidding at all. And you use learning rate of 1. Okay, anyways, no more secrets, otherwise, like, anyway. So to summarize, sequences are very important as a building block for many machine learning models. Everything, in a way, is a sequence. And recurrent neural networks are sort of a very nice way to vectorize context that allows us to scale up and learn very efficiently from data that is vanishingly scarce. Like if we want to learn models for every sentence, there's many possible sentences and very few that we actually realize in a data set. And also, there are model architectural tricks that allows us to deal with some mathematical issues with vanishing gradients, mostly due to the fact that we're multiplying matrices that are the same matrix many, many times, one after the other, with a nonlinearity in the middle. So with that, I'm just going to talk to you about some sort of extensions of these models that enabled so many different applications, and really you have to understand that intuitively all there is explained now, right? So the chain rule is very important, and recurrent networks can build amazing diverse set of things that before it was a bit sort of annoying to deal with regular deep neural networks or convolutional networks. So I really like this blog post by Andrew. He made RNNs quite popular by basically releasing also some open source. And he had this sort of mapping of, okay, now that we can have these green blocks that can deal with sequences, right? So you can think of these blocks as these LSTM, with all these weird connections inside, but forget about that. Then there are many applications we can start to think about that we couldn't before, right? So the one-to-one mapping, this was maybe the ImageNet, where the input was an image, the output was a class. We knew how to do that before recurrent neural nets, but now we can do all sorts of things, like, for instance, mapping many inputs to one output. So one of the models that we worked on was on video activity recognition. So here the problem is there's a video, it has many frames, many images, a variable number of, because videos have different lengths, obviously. And the model is kind of going to look at a whole video, and at the end of the video is going to decide which sport was present in the video, for instance, right? So this model sort of reads into the memory frame by frame, And this model needs to understand that when it sees a certain kind of ball, maybe this is a sport that relates with a ball, but maybe it sees a green field instead of a, like whatever, brown field, so it's maybe soccer and whatnot, right? And this model is actually state-of-the-art at video recognition, which is a useful thing to do on YouTube, because then you can automatically categorize all the uploaded videos to certain categories of sports and whatnot. So there are many such things, but one important distinction that's a bit technical, but what we've described so far is not, so these outputs that could be labels per frame or so on are not generally, it's a bit less powerful to see them as independent decisions per time step. So in language, we don't decide that there is a word without looking at what the previous words we output. We do this in a what's called autoregressive fashion. So perhaps a more generic picture of this is that, sure, we can receive inputs as sequences, so we can be given a video, we can be given any sort of thing, but the output of our model, I mean, if it's a single label, then it's a single label, but if it is a sequence of labels, it's useful for the model to be input back in what the prior label was. That is what the chain rule is. That's what we just described. So this making the models autoregressive generally helps a lot. And in very few cases, you want to have a model like this that predicts something, and then the next time step doesn't know what it predicted, right? Whereas this model would be input what it predicted in the previous time step. So this is crucial for language modeling. Otherwise, you would just be predicting what's the third word in a sentence, and I don't tell you what the first or second word are. I mean, you can take a guess, right? The third word is probably not the one that is capitalized, but maybe it is because it's a name and so on. Yeah.
Would it also make sense to feed in back the distribution instead of the sample?
It would. You would think it would make sense, except that the distribution actually is already encoded in the green box, right? So.
Well, depending on what the transformation is, it's from green to blue, right?
Right, so green, which is the hidden state, maps to, let's say, a softmax decision over 10,000 words. And if you fit the distribution of your own model, then there's no new information that you gain from fitting that back in, because that distribution was already encoded in the green box. But the sample actually is very important. The sample, because imagine, right, if I tell you, okay, I would say, I lived in San, and then I'm asking, what's the next word, right? Okay, the distribution, you don't need to see what the word was, actually, right? The distribution after the word San, let's assume there's only like San Francisco and San Diego. Then you say, okay, 50-50 is San Francisco, the other is Diego, right? So the fact that the next word could be any of these two words with 50% probability and 0 elsewhere, it's something that the model already, if it's converged, already knows. But now, which of the two actually I will pick is very important to then proceed to generating, right? So if I lived in San Francisco, you then should expect seeing Golden Gate, whereas if I lived in San Diego, which I actually also lived in San Diego, then you should expect to see maybe surfing and other things, more likely, right? So inputting the distribution, it's something you can try it actually, and we did try that, but the model already knows the distribution if it's been well trained. But definitely the model doesn't know what the word for that particular sample is, because there's uncertainty in language, as we were discussing earlier on. So now, like, what is actually, okay, so we have all these models. We have a large data set of news, right? This was trained on a data set called Google News Benchmark. There are 1 billion words in this data set, and the vocabulary size is not 10,000, but 1 million, actually. So there are quite a few variety of words, like Vieira, all capitals, and so on, right? So words are a bit of a messy domain. And what we did is just train one of these big LSTMs on each sentence of this corpus, and then we can sample from the distribution we trained a new sentence, and this is a bit of what came out. So half of these sentences are real sentences that some human wrote. The other half are just sampled from a very good model that we trained a couple of years ago. And if I disclose, I mean, this is a bit of mini Turing test, but the green ones are actually real, the red ones are from our model. And you can kind of see that these models are very good, but they miss still some very key important aspects of intelligence. So trying to do Turing tests with these models is fun, but also clearly not sufficient. So, for instance, the first sentence, some of the obese people live 5 to 8 years longer than others. It's a valid sentence, but it just doesn't make sense, right? So how can the obese people, I mean, we just know, like, I mean, how these models sort of try to model, like, words after the other and so on, and they do a reasonable job, but crucially, I think these models miss, like, there's some common sense or like some prior knowledge that we have that these models failed to really get. So to detect, but these models are very good. If you see these samples from n-grams, you would see sentences that really are clearly off, like they go in circles and do all sorts of crazy things. This model is pretty good. However, we can still see that they're not, I mean, or someone could expose exactly the truth while lying. I mean, they're fun actually, but not as good as, if we ask a writer, oh, can you write a possible sentence that we would encounter in the news tomorrow? Yes?
Just wondering, with the vocabulary size being so large, what did you do to deal with the softmax of the word?
Right. So this is sort of a bit of a tangential topic, but in a nutshell, you have a 1 million way softmax, and instead of, so you would have to maximize the probability of the correct word divided by the sum over all the 1 million rest of the words. Instead of summing over the 1 million words, which would require a very large matrix multiplier, we sum over only 8,000, which is called, like, it's an important sample softmax. It's a very simple technique, and the idea is that we don't need to make competition between the correct word that goes next and all the rest of the words. You can actually just subsample this rest of the words, and that speeds up the learning, and it still works quite well in terms of log likelihood. So we released this model. You can play with sampling from it, and you can prefix, you can start a sentence and then see what comes after and so on. And then one of the questions here is that we measure the log probability of sentences, or what's called perplexity, which is the branching factor. And these models, the best models are about 20 perplexity. What does that mean? That means that there's 1 million possible words that come next, and our models, every time they have to decide amongst 1 million, they're kind of deciding only up to 20, right? So they sort of discard almost all the words, but they still have 20 words of information that they don't know quite which word works next, right? So now these models are very good at assigning probabilities. Are we so good at this? I mean, I'm not sure we are as good as this model, right? If I ask you to start assigning what is the probability of this sentence, right, and I give you some random sentence, you probably are not going to do very well. But you definitely will tell me whether a sentence is sort of human or not human. And this poses a very interesting question, which is how do we evaluate these models? We train them to maximize the log probability for a given corpus, but this question is completely unsolved. There is a very interesting line of work on adversarial training, which tries to do not probabilities, but do I believe this is a real sample versus a fake sample that you just generated? But actually, these models work quite well for images, but not so well for text. So there's still a lot of research, and these are all interesting topics that if you want to discuss further, we can do so after or offline. So now, which do you think a language model, which simply takes sentences and trains on maximizing, which do you think fits here? Is it a sequence model, or is it an autoregressive model? Does it receive inputs or not? What do you think a language model is if you have to characterize it in one of these? Any ideas? Do people think is the last one, for instance? Many to many. Okay. So actually it's none, in my opinion, right? Because the problem is these models don't get any extra input, right? So they're trying to and that's where we're going to explain what sequence-to-sequence models are. But the model, right, it starts from nothing, right? So there's no input. And I'm going to ask, what is the first word that you think should go in the sentence? And then they generate one word, then you input that word back in, and then you say, what's the second word? And so on and so forth. So vanilla language models don't take any input. The only input they take is their own outputs, one at a time, and perhaps the very first token that they receive is beginning of sentence, right? So you typically have begin the sentence, and then you sample the first word, you input the sample, you sample the second word, and so on and so forth. So you can also model images, as I was saying, with a language model in mind. And I'm going to skip through this, but it's a very cool piece of research which essentially shows though how sampling works, right? So imagine you train a model to generate a set of pixels or a sequence of pixels, and we're now asking, okay, can we generate a new image from this distribution? Much like when you sample a new sentence, you want to sample like a new image, and I haven't described actually how sampling works, but it's important to understand how, right? So what we do is essentially sampling is very efficient because there is a very natural sequence. So we can sample using what's called ancestral sampling. And here the idea is very simple. We are going to sample the first word, or in the case of images, we sample the first pixel, right? And here you think of a pixel as a 0 to 255 word, which is the pixel intensity for the 3 color channels. So I start with a blank canvas, and the first pixel is this like dark pixel, okay? Then I sample the second pixel given the first one. I sample the third pixel given the first two, and so on and so forth, right? So I can keep sampling a model that I've trained to maximize the log likelihood of images. These are CIFAR10 images. And then you start seeing that as you sample line by line, you get pretty coherent structure that is fairly long-term, right? So I'm sampling here like this pixel, or maybe this pixel, and it kind of understood that many pixels ago, right, in one line ago, which is like 32, there was like some sort of vertical object there. And also, interestingly, then it assigns some probability distribution over the values from 0 to 255. So here, it's fairly confident, right? The distribution is fairly like concentrated around this value because it thinks, I mean, here probably there's a green pixel, right? I mean, the exact intensity is not clear, but it's clear that it's a green pixel here. If I ask any of you, that's fairly reasonable. Here, the model is a bit less certain what is the next pixel because it could be that is a pixel that is white, but maybe this thing actually was opening and there's like a black pixel, so it's actually think it's either white, this is actually a white with high probability, or any of these colors with some low probability, right? So you can start seeing how these models believe what comes next. This is for pixels, but the same happens with words, although words are like a bit messy to represent because there's many of them. Yes?
So in order to make this work, you have to impose an ordering over the pixel.
Yes.
And it seems that the choice of ordering is probably going to have an effect, because if you think that sort of one pixel will care about its neighbors most,
yes.
Actually, if I rastered more locally, it
yeah.
might help. Have you guys tried that?
So you might think the order obviously matters to some extent, but we try to raster like in vertical versus horizontal, and obviously there's a big discontinuity if you do like this, like we did, from this pixel to its neighbor. There's a long sequence to be like retained in memory, but there's a slightly smarter way to linearize an image, right, which is kind of a circular sort of raster ordering, and it didn't make any effect in terms of the log likelihood that we achieved was essentially the same.
And visually the pictures as well?
It's hard to assess, right, because again, these pictures look, you can cherry pick as well and so on, right? I mean, does this look like a real picture? I mean, it kind of like looks like something, but it's it definitely learned like obviously rules of images, like that there's blobs that have the same color and edges that cannot these edges sort of are relatively continuous and so on. So anyways, sampling is how we generate these text samples, or in this case a new image, but it is quite expensive because at any time we have to sample a pixel, then we have to take the pixel, input it into the recurrent neural network, and sample the next pixel. And the problem that if you do that is that you have you cannot batch anymore, which is more of a technical issue with the current hardware that we have. But it's actually a pretty big challenge that people tend to dislike these models because sampling is quite slow. And you can sample a bunch of images and you can assess how real these look, but definitely the model has learned about a wide variety of images, meaning if we sample, we see like something that looks probably like a bird and something that looks like a seashore and so on. And this is a very cool field to generate images. Many people are spending a lot of time in it. And then you can do other things like instead of sampling, you can say, well, the first half of the image, I'm going to give it to you, and then please can you autocomplete these? And these are all like samples from the model except for the first one. The first one is the ground truth, and the rest is how the model interprets the continuations, right? So the same way you can do continuations in text, you can do continuations for images. And in some cases it's okay, and in some it's not that great, but you can see definitely like it learned. I mean, you know, if I ask you to do that, I mean, I'm not sure. Obviously, we need to be painters to do this very well, but in general, these models are increasingly good at that you wouldn't recognize whether it's being painted by a model or it's actually the actual image. So there's lots of applications you can do with these, simply by taking these. The original actually wasn't this close, it's the last one, so even it fooled me. Interesting. So these models all generate sequences from nothing, so to speak, right? So they are trained to maximize the probability of observed sequences, and generation, except if we force sort of the first half of the image, as we did in the last example, they don't take any inputs. They just generate, you know, a sentence that looks like a real sentence. So a very important application was when was done for a particular kind of generative model that takes a sequence input as well. And it's really simple. This is the key insight from a paper from back in 2014, which was called sequence-to-sequence learning, is that, well, we can generate a sentence XYZQ, let's say, by the chain rule, but we can also generate this sentence conditioned on some extra information, right? This extra information, in the way we did it, and for the purpose of this research was to do machine translation, right? So I don't want to generate any English sentence. I want to generate an English sentence whose translation is some particular given input, let's say French, which was the data set. Actually, we did English to French, which was a bit annoying because I don't speak French, so I wouldn't know if the model was very good. But that was a standard data set, right? So you take an input sequence, and then you want to generate the corresponding translation, very intuitive task. And the way people were doing this was based on phrase-to-phrase tables. So, I mean, there were like lots of approaches. And honestly, the first time we tried to train a neural network to do this end-to-end, it didn't work as well as the state-of-the-art. But it was a very simple idea and a simple approach that worked so well that, and we worked on it for like just a few months, that we thought this, when we perfect these models, probably they're going to beat all the other statistical machine translation approaches. And the insight is essentially take a language model, so take the right-hand side here, and just condition it on not only the vectorized version of the previous words, right? So here, to predict z, we vectorized y, x, and underscore by this recurrent neural network. But there's also something else we vectorized, which is a prefix sequence that we didn't need to generate. It was given to us for free, which is the French version like of the sentence, for instance. So there's a recurrent network that is reading A, B, C, D. It doesn't need to do anything yet. It's just reading it, and it's the sentence we try to translate from. Now the state of the LSTM in this case is V, and from V, then we start saying, okay, now we're asking you to start predicting what is the first word of the English translation for this French sentence, and this would be X. And then given X, predict Y, given X, but also A, B, C, D, right? So if you write this in sort of the chain rule jargon, instead of having probability of a sequence Y1 to YT prime as the product of the chain rule, we add a V vector, which is vectorizing all the context from X1 to X3, which is an input that I give you for free. And that's it. Then it's the same code as language modeling, where you receive an extra few words at the beginning. And that idea that is so simple, you can train it on a large corpus of pair sentences, input, output. And that sort of like has all sorts of applications. And this is Isabel from here, actually, who was joking on Twitter that any NLP or natural language processing task, if you have enough data and so on and so forth, you can just apply sequence to sequence. And this is a joke, but there is actually a large set of things now that have been attempted with this kind of paradigm. And I'll describe a few of them with the remaining minutes. So now going back to this picture, sequence to sequence models are the many-to-many picture that is mostly here, or it could be here, depending on how you delay the inputs and the outputs. But for machine translation, here we have red boxes that are the French words until we reach the end of sentence. And then, in an autoregressive fashion, obviously, we start predicting the corresponding English translation one at a time. And a small aside here is that, okay, to train this model, we're going to see both the French version and the English version, right? We're given both. These are corresponding translations of each other. And we just train theta, the parameters of the model, to maximize the log probability of y1 to yt prime, the English words, given x1 to xt, the French words. But once I train this model, right, I want to now decode for a new given French sentence. I want to translate it, but I have no idea what the English translation is, because obviously if I knew, I didn't need to use this model. So decoding is a bit different, and it's just but it's very similar to what you do in sampling, but you're a bit more careful, and instead of just sample any next word, you pick the best word according to the model. So what you want to find is what is the best sequence of words in English such that they maximize this pre-trained model, right? So this model is trained to maximize the probability of pairs sentences. And now I'm going to give you a French sentence, and you can literally brute force search all the English sentences, and you want to pick the one that looks the best according to your model. That's going to be your translation. To do this exhaustively, obviously, is non-practical. You don't actually try all the English sentences. What you do is what people call beam search, which is actually fairly simple. So we're going to start by, okay, we are given some French sentence, and we have the probability over the first English sentence, okay? These are probability over 10,000, 1 million words, and we're just going to pick, if beam size was to be 2, we just pick the top 2, right? So our model, in this case, let's say, believes that the top 2 words are I and my, right? So these are how it believes the sentence should begin. Now, we try both inputting I and my as the first word to predict the second word. The model needs to be input the first word, remember, to predict the second word. And then we are going to look at all the possible sentences of 2 words that the model believes would be like possible. So let's say there's I decided, my decision, I thought, I tried. These are ranked by likelihood. So far, the model believes I decided is the most likely explanation, and my decision is the second most likely. And there's I thought, I tried, and so on. And then we're going to now drop everything but the top 2. So the beam size 2 means we always keep the top 2 hypotheses alive. So there's I decided and my decision. And now, again, we expand, we go to the third word, and so on and so forth, until we reach an end of sentence, in which case we say, well, the translation is over. And that's actually how machine translation at Google and so on works, which is essentially illustrated in this fancy diagram, but the diagram that is maybe more accurate is this. So this is how the model is. It's not a single LSTM, but it's a deep LSTM. I don't have time to go into the details, but it has also skip connections, and it has something that we haven't discussed, which is these attention mechanisms, which is extremely cool, and Alex will talk about this in a few weeks. But these attention mechanisms allow to not have everything in a single vector in the memory, but it has it distributed over time, which is a very nice addition to these models that was done in 2014 as well.
At training time, do you do the autoregressive thing, or do you feed in the ground truth?
At training time, because you observe the ground truth, you feed the ground truth. It's much like when you have graphical models, you would feed, at training time you observe everything, and then for inference you have to do belief propagation, this is an approximation method to get the max. Good. And, it worked well and so on. This is not important. But now going back to code, the cool thing is this model also is extremely simple to implement. In orange, we have the LSTM, which we know it's like a few lines of words of code. So these are actually a slightly different implementation that is open sourced, and the link is going to be sent to you later. And the rest of the code is actually almost the same as language modeling, where the first half just you don't predict from, so you just kind of are reading words happily, and that's it. And then the second half, you read words at training time, but then you have to predict the next word, much like you do in language modeling. So the code is extremely simple. And then, again, as I was saying, we start doing all sorts of things with sequence to sequence. So much like what we do in translation, which is probability of English given French, we could do now probability of English given image, which is sort of a weird language, so to speak, right? And the model look identical. You have this excellent cherry cake with one cherry on top, actually. And then you use some ImageNet model to kind of embed this weird word into a vector, much like you have French words and so on. This is a single word, it's a single word sequence, so to speak. And then the rest is just a language model that tries to decode what is the content of this sentence. And then you train it. This was quite amazing. I had this data set, and I just changed one line of code. I went to sleep. The next day, the model worked quite well. It could have been improved. Later, it was improved more, but the nice thing is this paradigm really is applicable to a very wide variety of applications. And this also is open sourced, both the weights and obviously the training paradigm and so on. And these models do quite well. Maybe you've seen this before, but there's actually an important message here, which is I did indeed train it with the gradient clipping of 5 and so on, and it worked very well. But it worked enough that it made me believe this model was going to learn how to caption any image. But actually fine-tuning and the kind of main pain point of deep learning is you have to sort of set the learning rate decays, and there's all sorts of hyperparameters, as I was saying in the first slide. So here, if you just don't tune the model too well, you get captions like the initial model, like a close-up of a plate of food on a table. This is okay. It definitely kind of gets what's going on. But if you actually tune the model much better, if you are more I'm participating in a competition, which we were, and we want to have the best captioning system, you really have to start finding what is the best dropout and so on. And tuning models go from essentially working badly or not working to working. And you'll experience this if you go into deep learning research or deep learning industry quite a bit. And you can see that just tuning, it was the same model, it was the same architecture, the same code, just tuning the hyperparameters made quite a big difference. For instance, a man cutting a cake with a knife, maybe that's more entertaining, but it's not really what this guy is doing. Same for this, a pizza sitting on top of a white plate versus a person is cooking some food on a grill. This is quite a weird image. And I honestly prefer the person eating a hot dog, but it actually is not a hot dog. And the point here is these models are very statistical. So actually, this picture actually is surprising the model work. But in general, if you have an image that is not like a common image you would see, these models fail. And what I like very much is there was a talk by someone from Microsoft that had this image of like a swimming pool, and it had a car, inside. And if I tell you this, any one of us can, there was a wild party last night and someone just drove into the swimming pool. Like anyone can imagine what happened. But what the captioning system said is a car driving down the road, right? Which is if it kind of sees a car, but these models really don't understand very deeply what these images are, right? It's very hard for any machine learning or statistical based model to understand the tail of the distribution, which we find super interesting, right? Like if it's a car driving in a road, I don't care about this image. I'm going to share the image that is most weird. So these models are failing at that, and you can definitely go to Google Translate and make the model fail the more you're out of the distribution that it's being trained on. So maybe that should be one of the homeworks, to make these models fail. Nonetheless, they're useful, you put them in production and so on. But anyways, they're better than anything else. So what can we do, right? But really, the example of this idea of surprise. So there was another image that was viral at this in the US, which was this squirrel that was on top of a bird flying. And again, I said I'm going to try my captioning system, and of course the thing said a bird on top of a tree branch, because there was some green background. So these models really sometimes give the false illusion of working, but they really don't work as well as we hope. And certainly we're far from passing Turing tests where we could actually try for looking for the weird answers that these models probably haven't seen in distribution. So here captioning would be maybe the one-to-many. We have a single image that is given to you, and then you produce a caption. And then you can also give a single label. So this is the same as the pixel RNN model, but now conditioned on a single bit, which is, not a bit, it's 1,000 labels. So it's essentially 10 bits or so. And it produces images now that are from a class, right? So we can do all sorts of things. We can also generate audio one at a time. with a model that is not exactly a recurrent neural net, where more like what Karen was describing, which is a dilated convolution. But it uses very heavily the chain rule, but it doesn't have this basically one single vector that is your memory. Now your memory to produce each of the samples is actually all the balls that affect the production of this orange ball here. And this also generates very natural speech. So, and perhaps like the obvious one that you're tempted to do, if you do language model, but you want to do sequence to sequence, you say, okay, I'm going to train a model to produce answers to questions, which you could attempt to say, oh, this may solve the Turing test. So we were a bit naive. We tried this. We took all the subtitle from movies, which has dialogues, one turn at a time, and then we feed our model, and we wrote a paper that was submitted to a workshop and accepted. And this was like kind of, so you could basically ask